Okay, this lesson is about the integral as an accumulator of change and the net change theorem. So let's think about the two equations that you've seen before. First, we've got the second fundamental theorem, F talk 2, which tells us that the integral of F is going to be equal to the net change, right, in big F, right? So the integral of f from a to b means the area under little f from a to b is going to be equal to the net change in big F from a to b. And here we're talking about y values, right? The y value of big F of b minus the y value of big F of a, right? Always remembering, by the way, guys, that little f is the derivative of big F, and big F is the antiderivative of little f. So that's an important equation, and we're seeing from that the area under a rate graph is equal to a quantity. It's equal to the net change of the quantity big F. Okay. Now, we can rearrange this equation, just add f of a to both sides, and then you get that f of b, right? So this is the y value at b on the big F graph, the antiderivative graph, is equal to the y value at a on the big F or antiderivative graph plus the area under the derivative graph from a to b. Okay, so this is what the two equations are saying, and this is the idea of the net change theorem, right? Here we see the net change, right? This is the net change in the antiderivative going from a to b. That is going to be equal to the area, right? And this is the idea of the integral as an accumulator of change. The integral, you can kind of see it as that area that is accumulating, being added up under the little f graph is really net change, which is being added up as y values on the antiderivative graph. Okay, let's take some examples to see how this works and to solidify that idea. So example 1 says the function r at the right models the rate at which spawning salmon swim up a river. R of t is measured in salmon per day, and t is measured in days since the start of the month. Approximately how many salmon swam up the river in the first 14 days? So we're noticing right away that we have a rate, and that's the graph. This graph represents a rate, okay, R of t. We have a time involved, right? So we're going from t is equal to 0 to t is equal to 14. And the question is asking how many. That's a quantity. So the question is asking you to relate a rate to a quantity, and you do that with an integral, right? So how many salmon, in terms of the picture here, really we're looking for the area. The how many is going to be the area under the rate graph. Let me convince you of that by just asking you to imagine that this graph, instead of being this curve, was just a flat line. Say there was a flat line here at 700. That would be saying that I had a constant R of t of 700 salmon swimming up this river per day. And if I had that and I asked you how many salmon swim up the river, find the quantity in 14 days, then you would be able to do that very easily. You would just go 700 salmon per day times 14 days. Answer is going to be 9,800 salmon swam up in those 14 days. And you also would know that that's this area. If you do 700 times 14, it's the area of that rectangle, right? So you can see that the area under the rate graph gave us the quantity, or the how many. So what we're realizing now with calculus is that that works even when the rate graph is not a flat line. Even when the rate graph is a curve, the area, which is the integral, it's this exact area, this purple area, is going to have the meaning of quantity, the net change. Okay, so I can write this answer like this. First of all, I would like to say that the exact number of salmon right, in those 14 days that swam up the river is going to be the integral from 0 to 14 of r of t. This is exact. That expression would be the exact number. We don't have an equation for r, so we cannot find the integral. We cannot do an antiderivative and find the answer, right? We have to just try to calculate this area as best as we can. And for that, I'm just going to use a simple, just approximations, right? So I'm going to look at this and I can say, okay, let me think of this as a rectangle here for that part of it. So 200 times 14. And then I'll use a triangle to estimate the rest of it, and I would get my approximate area, okay? So this is approximately equal to 200 times 14 plus 1/2 of 14 times 1300, and I would get 2800 plus 7 times 13, or 9100. So my final answer is approximately 11,900 salmon swam up the river in those 14 days. And we have used this idea of the integral of a rate being a quantity, right? So the integral we know gives us area, and as that area is adding up, you want to think about that as a change in the quantity of whatever is changing, right? The area represents change in some quantity. Okay, let's look at the next one. Example 2, water leaks from a tank at a rate of 2 plus 5t liters per hour, where t is the number of hours after 7 a.m. How much, see, there's your quantity, here's your rate, here's your quantity. How much water is lost between 9 and 11 a.m.? So first of all, if we're counting from 7, then 9 is t is equal to 2 and 11 is t is equal to 4. So the integral of the rate is going to give me the quantity from 2 to 4, right? And I just have to do the integral. So this is an example where I have an equation. So I'm going to find the antiderivative and find the exact area, which will be 8 plus 40 minus 4 plus 10, I think. And so my final answer will be 48 minus 14, or 34 liters, right? 34 liters is how much water is lost between 9 and 11 a.m. In other words, water is leaking from the tank, right? So the change in the amount of water between 9 and 11 a.m. is 34 liters. There are 34 liters less water at 11 a.m. than there were at 9 a.m. in the tank. That's another way to say that, okay? Example 3 is about velocity, right? So with velocity, we want to remember that, we've got our ladder and positions on the top. And so when you integrate velocity, right, you are getting a change in position. If you integrate a velocity from one time to another time, then you're finding the antiderivative, and you would be doing s of t2 minus s of t1 if you're going from time 1 to time 2, right? This is a change in position, okay, or a displacement. So the integral of the velocity gives you the change in position. Another way to say that is the area under the velocity graph gives you the net change in position, okay? So let's go here. Here we've got the velocity graph. You can see it's always positive, and we're looking for the distance traveled, right? So the distance traveled is really going to be s of 8, the position at time 8, minus s of 0. That's going to be the distance traveled, since the velocity is positive the whole time, okay? So if the velocity were not positive, then for distance traveled, I'd have to take an absolute value of the velocity and then integrate. But in this case, I can just think of my integral of the velocity is, that would be the exact, right? This would be the exact from 0 to 8. And that would be exactly this area, right? We don't have the exact equation, so we're going to have to just look at this and and calculate the number of squares, really is what it comes down to. And so we can do like this rectangle here is 3 times 40 or 120. And then we could just add up these little areas. You could do a triangle like this and think that's 1/2 of 4 times 40, so that would be 80. That's about 200. And then we've got up here about 2 rectangles, it looks like, because this little bit could fit in there, sort of. And so then we have 2 rectangles. So it's 10 times 2 is 20, that piece of it, right? So yeah, somewhere around 220. I think the closest answer would be that one, 210, okay? Yeah, so there again, we are integrating a rate, which is the velocity, finding area under a velocity, and that's going to be the net change in position or the distance traveled. Okay, let's move on to this one. So the cows on a small dairy farm in upstate New York are milked in the morning during a 2-hour period. Milk from the cows is pumped into a storage tank, and the volume of the milk in the tank at time t is measured by a strictly increasing twice differentiable function m, where m is measured in gallons and t is measured in minutes. At time t equals 0, there are 300 gallons of milk in the storage tank. Values of m at selected times are given in the table. Okay, so it's a table problem. M is in gallons. So the first thing to understand is that this is a quantity. It's not a rate. T is in minutes. Okay. Now, some of these are questions from the past, right? So connecting, as AP always does, all the different parts of the course. So find the average rate of change of milk volume over the interval from 0 to 120. That's an A rock, and it's just going to be, you want to write M of 120 minus M of 0 over 120 minus 0. So this is going to be 4250 minus 300 over 120 minus 0, and that's 3950 divided by 120, or 395 over 12 gallons per minute. That's the average rate of change for the 120 minutes. Estimate m prime of 70. So m prime of 70 is an instantaneous, right? M prime of 70 equals the derivative or the instantaneous rate of change. We have a table situation, so we cannot get the exact m prime of 70. 70 isn't even in the table, and even if it were, that would be m of 70. We want m prime of 70. So we have to go to the closest numbers, which are 50 and 90, right, and do average rate approximation. So m prime of 70 will be approximately m of 90 minus m of 50 over 90 minus 50, and this is going to come out to be 3360 minus 1640 over 90 minus 50, and this works out to be 43 gallons per minute. Okay, 43 gallons per minute. Okay, then we have, let's just take a look here at part C. So part C says, use the table to evaluate the integral of 0 to 120 m prime of t, right? So now m prime has been introduced, and if m is the quantity, then m prime is the rate, right? It's the rate of change of the volume, right, of milk. So it's a rate. So if we're integrating a rate, we're going to get the quantity. And you can, in a table problem like this, when you're given a rate, you want to realize that if you're doing the antiderivative of m prime, we don't know the equation for m. We don't know the equation for m prime. But we do know that m prime is the derivative of m. And so m is the antiderivative of m prime. So if I were doing this, I would be doing m of t and then evaluating at the top and the bottom. I would get m of 120 minus m of 0, right? So we're again seeing that the area under that curve of m prime is the net change in the m curve from 120 to 0. It's the y value difference on the m curve is equal to area under the m prime curve. So I just have to go here and do 4250 minus 300 to get 3950, and 3950 gallons is going to be my integral from 0 to 120 under m prime, and the units are gallons, and the meaning is that between these two times, 0 and 120, right, between t equals 0 and t equals 120, the net change in the amount of milk in the tank, right, in the, was it a storage tank? Yes, a storage tank was 3950 gallons. Okay, that's the meaning of that integral. Okay, use a right Riemann sum in part D with 4 subintervals indicated by the data to approximate the integral from 0 to 120. Notice now we're not integrating a rate, we're just integrating m, okay? And we'll, in the next unit, we'll understand what the physical significance of this integral is. Right now, we're just realizing that this is not the quantity. We are integrating. The quantity is already inside the integral. So this is a different integral than the one we did back here. But we can do this with a Riemann approximation. We cannot do an exact. Riemann approximation is just going to be your table approximation for, delta t's are here, and then we're doing a right Riemann sum, so we'll go here, 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 and here, and we'll write our m4, which will be, let's see here, it would be 20 times 780 plus 30 times 1640 plus 40 times 3360 plus 30 times 4250, okay? And this will be equal to 326,700, right? And the units of this would be gallon minutes, okay? Because this right here is in gallons and the dt is like in minutes. Okay, so getting here to example 5. Example 5 is a very important type of problem. It's a very important AP style problem, which is going to involve F-talk2 and the net change theorem. But it is also going to involve a lot of review of things we've done before. So let's break this down. We have a continuous function g. It's defined on this interval from -4, which is here. So wait, -4 is here. And we're going until 10. And it's a piecewise function. It's made up of 3 line segments. And those are here, 1, 2, 3, and a semicircle, which is here, right? So read the question and understand that that's what we've been given. And we're being asked for first many different things, okay? So the first thing is the average rate of change, which has, some of these things have nothing to do with F-talk or NCT. They're stuff from before, right? So average rate of change we know is just y2 minus y1 over x2 minus x1. So first of all, this is g of x. So let's just write that in big letters. So a rock for g of x is going to be on this interval, right? Here's my x1 and x2. So I'll do g of 4 minus g of -2. This means y2 minus y1 over x2 minus x1. And then this is the g graph. So I go on the graph to find that g of 4 is -4. And g of -2, that's here, is 5. And then I divide it by 4 plus 2 or 6. So I'm going to get -9 halves. -9 over 6, I'm sorry, which is -3 halves for my average rate of change. Okay, the next question says, suppose j is the function such that j prime of x equals g of x, and j of -3 is equal to 5, find j of 8. So this is a case where we've been given an antiderivative, right? If j prime is equal to g, then you take a derivative going downwards. So j prime is equal to g, right? That's how they are. So then j must be the antiderivative of g, okay? So if j is the antiderivative of g, then I know that I can use my net change theorem. The net change theorem says that the antiderivative j at 8 will be the antiderivative at -3, right, plus the area under the derivative going from -3 to 8. And so this is, using our net change theorem, right? And that's from the box at the beginning of the lesson. So now we know that j of -3 is 5. We also know that j prime just means g. So we are just finding the area under the g graph going from -3, which is here, to 8, which is there. So I have to think of, I'm going right, this triangle right here, this green triangle, the area of that will be 1/2 of 3, which is the base, times 5, which is the height. So this will be 15 divided by 2 is going to be my area here, right? So this area is 15 over 2, 15 halves for this green part. And then here I have a semicircle of radius 4, diameter is 8, radius is 4, right here. And so this semicircle will be pi 4 squared divided by 2, which is 8 pi, and it's going to be negative because I'm going from 3 to 8, so my direction of integration is that way, and this is under the axis. So this out here is going to be 5 plus 15 halves for the triangle minus 8 pi. So 15 halves is 7.5, so I can say this is going to be equal to 12.5 minus 8 pi for that part of the question. Okay, this next one is about sketching the antiderivative, right? Sketching, this j was an antiderivative, and now they are actually defining an antiderivative again, just doing it a little differently. They're telling you that big f of x is an area function, right? Big f of x is the area function under the g graph. So we know that the area function is the antiderivative, right? This area function, this guy, is going to be the antiderivative of that guy, okay? And we know from our f-talk 1 that if you take the derivative of this equation, so if I do f prime, right, do a d dx of this, remember that you basically get g of x from f-talk 1. So you need to write this on your paper. Big F prime is equal to g. You have to say that somewhere. That's telling the reader that you are realizing that big F prime is g. This graph is also g, so that means this graph is big F prime, okay? And so now we can answer our questions. Well, first they want us to sketch a graph of f, right? So this is big F prime, and I'm sketching a graph of big F. So we're doing exactly the same thing we did in the fall, okay? And let's just review how to do that. So in the fall, we said things like, let me just jog your memory. We said, for example, that when big F prime is positive, then big F is increasing, right? Now remember, F prime is equal to g here. So that's when this graph you're seeing is positive, the antiderivative F is increasing. If g is negative, if big F prime is negative, then F is decreasing. If F prime is increasing, right, then F is concave up. If F prime is decreasing, then F is concave down. If F prime changes from a positive to a negative, F has a relative max. If F prime changes from a negative to a positive, F has a relative min. if f prime changes from increasing to decreasing or decreasing to increasing, then f has a point of inflection, right? So these things are not new. These are relationship between a derivative and an antiderivative, right? And we covered that in the fall. What is new is that now we're going to know how much f increases or decreases. That's the net change, right? So let's talk about f a little bit more. So f, from the question back here, f is this area function, right? This guy right here in blue, that's f. So f, let me write it here. They gave us it's equal to the integral from 0 to x of g of t dt, right? It is an area function. We're finding area under g. So let's just do a few of these, right? Let's do f of 0, integral from 0 to 0. You're not moving anywhere, so when you calculate area from 0 to 0, the answer is 0. That's also saying that if you have a definite integral where the upper and lower limits are the same, then the answer is 0. Let's do f of 4. So f of 4 means, let me just write it down, integral from 0 to 4 g of t dt, right? So we're calculating area in this graph going from 0, starting at 0 and going rightwards until 4, right? So then I will have this half circle, quarter, half of the half, quarter circle, and it's below the axis, and so it will be equal to, the circle was a radius 4, and I need only a quarter of that, and I'm under the axis, so I'll end up with negative 4 pi for that. F of 8 is, we're going now from 0 to 8 g of t dt. So now I've covered the whole half circle, so the area of that is negative 8 pi. F of 10, let's think about f of 10, right? Here I'd be starting here and I go all the way to 8, and so big F of 8 is negative 8 pi, and then I now have to add in this area here, right? This red area here, which is the area of a triangle. This triangle area is 1/2 of 2 times 4, or 1/2 of 2 times 4, which is 4. Okay, so then I have to add in 4 to my number that I had before at f of 8. So f of 10, you can think of f of 10 as basically it's the area until 4 plus the area from 4 to 8 plus the area from 8 to 10, right? And this is all going to add up to negative 8 pi plus 4, okay? That's my f of 10. Let's think of some negative numbers for x values in the f function. What if I did here f of negative 3, okay? So f of negative 3 means I'm starting here and I'm moving backwards, so that's a negative sign, and then the area is above the axis, right? So it'll be f of 0, which was 0, minus 15 over 2. So f of negative 3 is going to be negative 15/2. I also want to show you that you can think of each of these as f of negative 3, for example. It's equal to f of 0, which we know is 0, plus the integral from this starting position to this ending position. So from 0 to negative 3 of f prime of x dx. And then since this is 0 and this guy is nothing other than our g function, that's why we're sitting there and calculating areas under the g function, okay? And we just have to keep track of which way we're going. We're always going from the bottom to the top, and whether the area is under or above the x-axis. Let's do one last one. Let's do f of negative 4. So now I'm going to be here, right? So I started at 0, and then I was at negative 15/2, and now I'm going to have to add in this area here. And I'm saying add because here's a case of two negatives that are canceling, right? I'm moving backwards, but the area is under the axis. So that skinny triangle, 1/2 of 1 times 5, or 5/2, this area right here, this guy 5/2, is going to get added to the negative 15 halves. So f of negative 4 is negative 15 halves plus 5 halves, or negative 5, negative 10 over 2. Okay, so now what have we done? We've calculated the y value on the antiderivative at all these different places, right? At all these different x's, we now have our y values, okay? So when we are sketching the antiderivative, what we want to do is the following. Let me just erase all of this so I can kind of show you how to do the sketch. First thing is, make sure you write somewhere on your paper that you have recognized that f prime is equal to g. This is a graph of g, right? So you need to say big F prime is equal to g. Okay, now to sketch the antiderivative, the first thing I want to tell you is that very often the scale on the antiderivative graph, scale of f, is not going to be equal to scale. So let's say not equal to scale of this G graph, right? So what do I mean by that? What I mean is, I know f of 0 is 0, so let me place a point here, right? This red graph is a graph of big F. Now, f of 4 has to be, from what I just figured out, has to be negative 4 pi. That's what we figured out back here. F of 4 is negative 4 pi. Now, negative 4 pi, so f of 4, f of 0 is 0, f of 4 we figured out was negative 4 pi. That's about negative 12, right? Negative 12 is kind of off of this graph because this is just negative 6 over here. So we're just going to sketch it like this. I'm going to say, let me just draw a point here, right, and call this y value negative 4 pi, right? So I'm at 4 comma negative 4 pi. So I'm using a different scale on my y for my red graph. Okay, then f of 8 was negative 8 pi, so that is, about negative 24, it's double of this number, and we're going further negative, so I'd be down somewhere here for that one, right? So it'd be 8 as my x, and the y is negative 8 pi. Remember that this right here is not on this scale. This is negative 6, but that's the scale for this graph. We're using a different scale for the red graph. Okay. Then I'm going to put down f of 10, and that was equal to negative 8 pi plus 4. So, negative 8 pi is like negative 24. So if all of this is negative 24, I'm coming back a little bit further up. So at 10, I'm at negative 8 pi plus 4. Okay. Then I go to my other side. I figured out negative 3, right? So f of negative 3 was, if I remember right, it was negative 15 halves. 15 halves. So, or negative 7.5. So let's make a point for that, right? So let me just erase this. That's not a point on the F graph. So negative 3, negative 7, 0.5. We'll put it there, okay? And then I have f of 4, negative 4, that's here, right? This is negative 3, and that was negative 5. So we'll put it like here, okay? So these are points on my F graph, on my antiderivative graph. So now to sketch the antiderivative, I'm going back to the fall semester, right? And I'm thinking about, let me just write this down, and I'm thinking about this table. When f prime is positive, f is increasing, etc. So I come here, and to connect this point right here with this point, I will think, well, the derivative here, f prime, which is g, is negative, and it's more and more negative. So I must be concave down between these two points on my F graph. Then I'm going from there to 8, and on that stretch, my F prime is still negative, right, over here, this stretch here. I'm still negative, but it's less and less negative, so I'm concave up like this, okay? Then from there, I go to a positive now. This is a stretch where f prime is positive, so then f is now increasing, and since it's f prime is more and more positive, I must be concave up. F prime is increasing, so f is concave up. Okay, let's go back here. And when you're doing this negative side, it's easy to get confused, right? So let's start at the leftmost point right here, right? And notice that f of -4 was -5 over here. This point right here is -4, -5. And then this point right here was -3, -7.5, right? And I need to be basically decreasing, which means f needs to be decreasing because f prime is negative, right? So that makes sense here. F prime is here, it's negative. F has to be decreasing. It's going to be decreasing in a concave up way because the slope is getting less and less negative. So it's going to do something like this, right? And then from there, it's going to start increasing because the slope went positive, right? So it's going to be going up. And then when it gets to here, this is going to be a point of inflection. And from there, after that point of inflection, it's still increasing because this is still positive f prime territory here. But it's positive in a decreasing way, right? So it's going to be concave down. So it's going to do this, okay? Okay, so what have we done here? We have connected the antiderivative to the area under the derivative. So that's what all this was about. We were able to calculate all these different values on the antiderivative graph. And then we reactivated your knowledge from the fall semester about the shape of the antiderivative, the shape of f once you know what f prime is doing, right? So we realize the graph we're looking at is f prime, so we can use all of that knowledge to get our f graph. This does take a little bit of practice, so please practice it and really understand it before you get to the test. Okay, so you can even just look at this graph that we drew for f and answer question number 4, right? You can look at the graph and realize that the absolute minimum of f is at 8, -8 pi, right? So we could even just look at that graph that we drew and understand that. And let's just explain that a couple different ways. The right way to do the problem, which we're going to do, is with a candidates table. So I'm going to remind you how to do that. But without even doing that, let me just write f of x is equal to the area from 0 to x under the g graph, right? This is what we know about f. Well, if you look at area and you think of, well, I'm starting to accumulate area here at 0 and I'm moving this way, well, you can see that the area is going to, that number, the accumulated area, net area, is going to be negative all the way until you get to 8. It's going to be more and more negative because you're accumulating more and more negative area. Then from there, you're going to start adding in a positive piece for this stretch here from 8 to 10. So the area graph's going to come up because you're going to cancel some of that negative area. So that means you've reached a minimum there, right? You're going to reach a minimum there. The only question would be, are there any other places where you would reach an even lower minimum, right? Because absolute minimum means the lowest minimum. So then you have to look at the other side and you have to realize, well, yes, this here is going to get subtracted off when you move left. So the graph's going to go down, here. But it's not, this area here is not anywhere near as big as that circle area. So you're not going to get to a lower point than -8 pi. This only got to -7.5. -8 pi is somewhere near like -24. So you can just look at the areas and sort of common sense understand where you're going to have your absolute minimum or maximum, and then you can justify it with the candidates table, right? So with the candidates table, this is like in the fall, you want to make the candidates table every time you're asked for an absolute minimum or maximum. So you put x and you put the thing you're trying to minimize, which is big F, right? So put the function here, big F is equal to the integral from 0 to x g of t dt. Okay, and then we're going to put in our endpoints, -4 and 10. And our critical points. Critical points are going to be where big F prime, which is equal to G, is either 0 or DNE. Okay, so big F prime is equal to 0 at x is equal to, let's see, 0 right there, and right there, right? So -3, 0, and 8 would be my three places, -3, 0, and 8. There are no places where big F prime is a DNE. Big F prime being a DNE on this graph would have had to be a hole or an asymptote, right? And I don't see any of that. Don't be thinking this right here is a place where big F prime is a DNE. Big F prime is equal to this graph, right? This place is a place where the derivative of G, so G prime or F double prime is a DNE, right? But it's not a place where F prime is DNE. Okay, F prime exists at that spot. It is equal to 5. Okay, so anyway, back here, we already calculated F for all of these values, right? It's just a matter of putting in the upper limit of that integral, and we did that. We did that back here, right? We did f of 0 and f of 4 and f of 8 and so on. So we pretty much have all these numbers. So let's put them into the table. F of 0 was 0. F of 8 was -8 pi. F of 10 was -8 pi plus 4. F of -3 was -7.5. And F of -4 was -5, right? So we want to put these numbers in, and in fact, you want to show this work, right? I had already done this work on the side, but you want to show that how did you get those numbers. Okay, so then you look at these numbers and you go, which of these is the smallest? And it's clearly this one, right? This is going to be your smallest number, and so that is where we have an absolute minimum. So we confirmed that. We already knew that looking at an area idea, but you can also justify it with the candidates table, and you should know how to do that. Okay, next one is find the x-coordinates of all points of inflection on the graph of f. So f has a point of inflection when f prime changes from increasing to decreasing or decreasing to increasing. Okay, I'm abbreviating. You would want to write the whole word out on a test. And so where does that happen? Let's take a look. It happens here, happens up here, right, at x is equal to -2. It happens here. Careful with circles. At the bottom of a circle, you go from decreasing to increasing at the bottom of that circle. And I think that's it, right? So we'll have x is equal to -2. So we change from increasing to decreasing at x equals -2, and we change from decreasing to increasing at x equals 4. And let's look at the graph of f, of f. It's right here in red, and you can see curvature changes there, point of inflection, so it's a POI, and curvature changes here. That's another POI, right? So if you drew the antiderivative correctly, then everything should line up. Okay, on what intervals is big F decreasing? F is decreasing when F prime is negative, and that happens on -4, -3 union 0 to 8. Okay, so that's just looking at the graph and seeing where the F prime or the G graph is negative. Last question for this is, let h of x be the integral from 0 to x squared of g of t dt. Find h prime of 3 and h double prime of 3. So we're recognizing this is an area function, right? So to get h prime of x, not only is it an area function, it's a composite area function, right? So we're really doing d dx of this thing. And from our last F-Talk 1 lessons, we know that we do that by putting this number in here, this expression in there, and then multiplying by the derivative of x squared, which is our inside function, right? So then I can do big H prime of 3, which is g of 9 times 6. 2 times 3 is 6. G of 9 off of the graph, I think, is 2. And so 2 times 6 is 12 is going to be my answer. Yeah, g of 9 is right here at 2, okay? All right, last one here, h double prime, right? So if you have h prime, now again, this is not really, well, I guess there was a little bit of fundamental theorem in here, but now we're doing, it's like, it's first semester. You're just looking at a function and thinking about how do I differentiate, right? And you know this is a product, so then h double prime of x is the first times the derivative of the second plus the second times the derivative of the first. This is a chain rule here, right? This is going to be a chain rule. So out prime of in times in prime, okay? So then I do big H, h double prime of 3, it's 2g of 9 plus 2 times 3 times g prime of 9 times 6. So I'm going to get 36, 6 times 6, 36 g prime of 9 plus 2 times 2 because g of 9 was 2. So I get 4 plus 36 g prime of 9. So then I have to go to the graph and think, how do I figure out g prime of 9? Well, 9 is here, and luckily g is a line here, right? So g prime is just the slope of that line. So g prime of 9 is equal to 4, rise of 4, run of 2. G prime of 9 is 2. So this answer here will be 36 times 2. 72 plus 4 is 76 for our h double prime. Okay, this is exactly like the other problem we did, but just to practice one more like this because it's a very important type of problem. The graph of f shown above or shown to the right consists of a semicircle and two line segments. If g of x is the integral from -2 to x of f of t, use the graph of f to answer the following. So first we're just finding a few g values, right? So g, it's an area function. So g of -2 is -2 to -2. Practice writing out these integrals, guys, properly so that you can justify your answers. It's important to be able to not just write down the answer 0, but show where it came from in terms of an integral. Okay, then g of 0 is going to be the integral from -2 to 0, g of t dt. If you look at the graph, you're starting at -2 and you're going to 0 and calculating this area right here, right? So that is just quarter of that circle, which would be pi, radius is 2, so it'll be pi times 2 squared divided by 4, pi 2 squared over 4, which is just pi. Okay, it'll be positive because I'm moving right and I'm above the axis. Let's see, g of 2 will be just integral from -2 to 2 of, I've been writing g. I've got to be careful with my own integrals. We're integrating area under f, right? F is the graph name, graph of f. Okay, so -2 to 2 would be, well, it's all of this area, right? The whole semicircle now, and that would therefore be pi r squared divided by 2, and I'm still positive, so this will be 2 pi for that one. And then I have g of 6, and so g of 4 and g of 6. I'll put them up here, g of 4. G of 4 means I've integrated now this this triangle here, okay? And that's a triangle 1/2 of 2 times 4, so that's going to be area 4 for this triangle here. Let's just keep track here. This was pi and another pi and then 4. So I have 2 pi plus 4 for g of 4. 2 pi plus 4 plus 4. And then g of 6 is the integral from from -2 all the way to 6, f of t dt. And that is equal to, well, so we can see that these two triangles right here are equal areas. You know, it's funny, they didn't draw it particularly well, but if you look at this line 4, 4, and 6, -4, then that's a line of slope, 8 down for 2 over. So it's a line of slope 4. So that means that this really is 5, even though it doesn't quite look like that. right? This right here has to be the point 5, comma 0, okay? And so these two triangles have the exact same area, and they cancel each other out. And so this will be the same as g of 4, which is 2 pi plus 4. Okay, now find the intervals where g is increasing. So this is the place where it's very super important, very super important that you say that g prime of x is equal to f of x. You would need to say this. Say it more than once. Definitely say it. How do I know that? I know that because here's an area function. And so the fundamental theorem tells us that the derivative of this area function is the integrand, right? So g prime of x is equal to f of x. You may want to then come to your graph and write it there as well. This is the graph of f, we know that, but we now know that that is the same as the graph of g prime. Okay, so then we can make the statement that if g of x is decreasing when or if g prime of x, which equals f, again, it doesn't hurt to repeat it, is negative, okay? And we know that that is happening on 5, 6. Okay, that's here. This is the only stretch where g prime, which is equal to f, is negative. Find the intervals where g is concave up, right? So again, g prime is equal to f, right? So g of x is concave up. Sorry for my scribbly handwriting. I'm trying to write fast. G of x is concave up when g prime, which equals f, is increasing. And that happens on two stretches. Right here, we're increasing, and right here, we're increasing, right? So from -2 to 0, union 2 to 4. Okay. Find the absolute extrema, right? So both maximum and minimum of g on this interval, right? So we're setting up our candidates table, and we're thinking of our endpoints. These are my endpoints. And then critical points. Critical points are places where g prime is equal to 0. Notice we're finding the extrema of g. So critical points are where g prime is equal to 0 or DNE. G prime is my graph. So I look at this graph and I go, there's no DNEs, and there's a 0 here and here. So I put 2 and 5 into my table. Okay, so this is, of course, our candidates table, and we're going to do this in a minute, right? But remember, also use common sense and think g is the antiderivative. It's the area. So if I look at this graph, I'm starting my area calculation at -2, and you can already see that you're going to reach a maximum area right here at 5, right? Because the area is going to be 2 pi plus 4 plus this area of this blue triangle here, right, which is 1/2 of 1 times 4, so it'll be 2, right? So I'll have an area of 6 plus 2 pi when I get to 5, and then after that it's going to go down, right? So I already know the answer. The answer is going to be 5. I just have to show that here, right? So here it would be good to actually write the integrals, because that's what you're doing. Like here, -2 to -2 f of t dt is equal to 0. Then you can say here, -2 to 2 f of t dt is equal to 2 pi, right? And then here, -2 to 2 f of t dt, to 5, I'm sorry, 5. It's to this x value. The x value goes in at the top, right? This is going to be 2 pi plus 6, I think we said, back up there, those two triangles. Yeah, 4 plus 2, 6, okay? And then at 6, we go back down, right? Because when you get to 6, you cancel out some of that area. So it goes back to 2 pi plus 4, okay? So here's your maximum, right? The maximum. Oh, the question, though, said maximum and minimum, right? So we're gonna end with absolute max at 5 comma of g of x at 5 comma 2 pi plus 6. Absolute min is actually going to be at -2. because we never go into enough negative area to make the whole number negative, so the lowest number is 0. So at 2, negative 2 comma 0, right, will be my absolute min. Okay, find the points of inflection of G. So G of X has a POI when G prime, which is equal to F, changes from, let's see, increasing to decreasing. That happens here at X is equal to 0, and it happens here at X is equal to 4. So we can write it this way: increasing to decreasing at X is equal to 0 and X is equal to 4, or from decreasing to increasing at X is equal to 2, right? That's a place where we change from decreasing to increasing. Maybe I should use the word and right here just to be safe, right? So because we have basically points of inflection at X equals 0, X equals 4, and X equals 2. Okay. Sketch G of X on the interval negative 2 to 6. Okay, so for that one, we're going to come here. I want to erase some of what I have here to make it a little less busy. Okay, so we're going to erase this, and I'll show you how to sketch this. I would leave here graph of F, which is equal to G prime, because that's the whole basis of our whole analysis, right? Okay, so we want to start with those G values that you figured out, right? Like we figured out G of 0 is 0. So put a point in there, right? Remember, the scale on your G graph is probably going to be different than your scale on your F graph. Okay, G of, I'll write the numbers here. So G of 0 we figured out was pi, because this circle here had area pi, right? So then I can say that by the time I'm at 0, I want to be up around pi here, right? This is pi. Okay, and then when I get to 2, I want to be at 2 pi. So I'd be up somewhere here, about the same height, right? If this is pi, then 2 pi is probably somewhere there, right? So this, now I'm at height of 2 pi. Then, so this is G of 2. Then when I got to 4, G of 4 was 2 pi plus this triangle here, right? This first triangle, and that was a half of 2 times 4, so it was 4. So it's 2 pi plus 4. So I'm 4 higher than this, right? So I'm up somewhere here, right? This is 2 pi plus 4. Actually, it's probably a little bit lower, right? 2 pi is about 6, so somewhere here, 2 pi plus 4. Okay, and then at 5, I still am higher. I'm at 2 pi plus 5, okay, because I've added in this guy. Okay, so I'm now somewhere. So line up your X values, so I'm up here, right? This is, I should make sure you're understanding that I'm lining up my X values, right? So here, for example, I'm trying to be right above my 4. I'm just a little bit off. Let me move it over. So here, right? This is the 4 comma 2 pi plus 4. This right here is 2 comma 2 pi. This is 0 comma pi, and now here I'm at 5 comma 2 pi plus 5. Okay, probably should be a little lower than that. Okay, I mean, I'm not making my Y scale super exact. Okay, I'm trying to line up like that. Okay, and then at 6, I've come back down by exactly however much I went up between 4 and 5, right? So I'm back down. By the time I'm at 6, I'm here, exactly to the same level as that one. So those are my G points, and now I have to think about the shape. I have to go through these points with the right shape. So between negative 2 and 0, G has to be increasing because G prime is positive. G prime is increasing, so G has to be concave up. So I got to be concave up. Then G prime which is this graph, is still positive, right? So G, which is the green graph, has to be increasing, but in a concave down way from 0 to 2. Then I have to go from 2 to 4, and now my G has to be concave up again, right? And then I have to go from 2 pi plus 4 to 2 pi plus 5 in a concave down way, right? Because look here, the slopes are going down, right? So slope has to go down. And then I have to come down, because I've now got a negative slope down here. I have to come down like that, okay? So this is how you draw the graph of the antiderivative, and you can check the things we said before. The absolute maxima, right, is at 5 comma 2 pi plus, oh, why do I have 6 up there? Oh yeah, sorry, this is 2 pi plus 6, not 2 pi plus 5. I'm sorry, I wrote the wrong thing here. Let's just fix that little error. That's because going from 4 to 5, this triangle has an area of 2, not of 1, right? I wrote it correctly down there, and then I changed it here by mistake. So this is 2 pi plus 6 as the absolute maximum of the graph, okay? And the absolute minimum, you can see, is at negative 2, okay? This is a closed graph with endpoints at negative 2 and positive 6. Okay, so that's that question. Okay, just a couple more. Given that G of 4 is 4, use the net change theorem to find G of 6. Now, there's a typo here. This should say given that G of 4 is 2 pi plus 4. Use the net change theorem to find G of 6. We've kind of already done this, but we found G of 6, right? We know G of 6 is equal to, again, it's just back to 2 pi plus 4, right? But the net change theorem, we could say G of 6 is equal to G of 4, right? This is like the ending x value. This is the starting x value, plus the integral from the start to the end of G prime, which is f dt, right? So this right here is the area from 4 to 6, which we realized was like there's a positive triangle and a negative triangle, so it came out to be 0. So that's why G of 6 is equal to G of 4 plus 0, or just G of 4. Okay, this last one is very similar to the last one on the last example. We have an area function k, and we're trying to find k prime of 1. So let's start with k prime of x. So the derivative of this guy, which is k prime, will be just plop this in, right? So it's f of 3x times 3, out prime of n times n prime. And then you just do k prime of 1 be 3 times f of 3. F of 3 from the graph is f of 3. So you have to think about f of 3. If it's 4 up here and 0 here, that's a slope. This thing has a slope of 2, which means that when x is equal to 3, that's 1 over, it must be 2 up, right? So f of 3 is equal to 2. This point would be 3 comma 2 on the f graph. So then I say this is equal to 3 times 2, or 6. Okay, and then k double prime of 1, well, let's do k double prime of x. We're differentiating k prime, so it's a product. Actually, it's not a product, it's a constant. So 3, and then it's a chain. So 3 times another 3 times f prime of 3x. And so we'll get 9 times f prime of 3x. And if we're doing k double prime of 1, it'll be 9 times f prime of 3. F prime of 3, we just figured out that slope. It's equal to 2. And so this answer is equal to 9 times 2, or 18. Okay, and that is it. That's a really long video, but these are some complicated questions, and I hope that you practice them really well and understand them well. Have a great rest of your day.